Okay, well, we're on to the last section of chapter 6, which has to do with writing what are called electron configurations. And we can draw an electron configuration like this, in which we draw lots of boxes and put lots of arrows in them. That's kind of a labor-intensive, time-consuming thing to do if we're trying to write an electron configuration. And so we have a way of actually condensing this down into a notation uh, that is fairly easy to follow once you understand how it works. And so, I'm sorry, let me just get through this slide. So let me show you what that would look like. You can write notations. So electron configurations are simply a shorthand kind of notation of communicating all the information that was in that orbital energy diagram. So we can take an orbital energy diagram like this, and rather than having to draw all these boxes and all these arrows and label them all as 1s or 2p or whatever it is, we can condense it down into a thing that looks like this. And so I've given you some examples, and then we'll talk about how to actually do it. So for example, as it turns out, the electron configuration notation for calcium, for some reason this is like a timed slide that keeps flipping to the next slide, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And for zinc, I could actually, and we'll talk about something in a second called the noble gas shorthand. We could simply write zinc as argon in brackets 4s2, 3d10. Okay, so I've told you that these are the notations that correspond to these elements. How did we get there? The first thing to do is simply to take one of these little things, say a 4s2 or something like it, and explain what that means. So so we're going to take an example of 4p5, and so the term 4p5 tells you about these slides just keep advancing on their own. This came from the publisher slides. The 4 in the 4p5 tells you that this is at the principal energy level of 4. So that's what the 4 is. The P in the 4p5 tells you what sort of subshell it is. It's the P subshell. And then the 5 tells you how many electrons are in that subshell. So I got a little bit thrown off by these slides advancing themselves. So let me just go back and do it again. If I wrote 4p5, what that means is I'm talking about all the electrons that are in the n equals 4, L equals 1, that is P subshell, and that there are 5 of them. Okay, so let's go back and figure out how to populate an orbital energy diagram and then turn that into into an electron configuration notation. And so here we go back with our blank orbital energy diagram, and let's consider chlorine. Chlorine is element 17, and so therefore an uncharged atom of chlorine has 17 electrons. And so we're going to populate this diagram with 17 electrons. 1, 2, 3, 4, 5, 6, 7. Notice we're following Hund's rule. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, that is my orbital energy diagram populated with 17 electrons in the ground state. But I don't like to have to do this every time. It's a lot of handwriting. And so what I'm going to do now is say, well, what I have in this box down here can be abbreviated as 1s2. At the 1s level, I have 2 electrons. What I have in this box can be abbreviated as 2s2. At the 2s level, I've got 2 electrons. What I have collectively in these 3 boxes, I can abbreviate as 2p6. At the 2p level, I've got 6 electrons. And then 3s2, and then finally up here at the very top, at the 3p level, I've got a total of 5 electrons. Now I simply take all of these things as I've got written there and just move them down onto the same line. And so therefore, the electron configuration written out for chlorine would be 1s2, 2s2, 2p6, 3s2, 3p5. We can further use what's called the noble gas core shorthand for this. And so, let me show you what I mean by that. First of all, we want to define the difference between valence electrons and core electrons, which of course is a really, really important point, and goes to everything having to do with bonding and structure and shape that we're going to be talking about in the subsequent chapters. Valence electrons are electrons that are at the highest principal energy level. And then core electrons are everything else, all electrons that are in lower energy shells. And so when we're writing an electron configuration notation, this is more convenient than this, but we can do something more convenient still. That's because we can write this out for chlorine, which I just had, 1s2, 2s2, 2p6, 3s2, 3p5. But we can take advantage of the fact that the core electrons, that is the non-valence electrons, essentially correspond to all of the electrons of a neon atom, right? Because 1s2, 2s2, 2p6, which comprises all of our core electrons, that's the electron configuration for neon. So I can simply substitute this equation into this equation, and that tells me that I can write the electron configuration of chlorine in the noble gas shorthand as neon in brackets followed by 3s2, 3p5. Now, it doesn't really gain me a lot here. It gained me some, but you can appreciate that when you're talking about something like silver, in which you had to write out the full electron configuration notation for silver, it would look like this, and that gets a little bit tedious. But you can also take advantage of the fact that the previous noble gas, which is krypton, it consists of everything from 1s2 through 4p6, and so I can rewrite silver as simply krypton in brackets, which gets me all the way up to 4p6, and then 4s2, 3d9. So speaking of valence electrons, here is a periodic table in which all of only the valence electrons are shown. And so each period starts with the core of the noble gas before. And so if we were writing the electron configuration for lithium, it would be helium followed by 2s1, beryllium followed by 2s2, etc. If we were writing it for magnesium, it would be neon followed by 3s2. If we were writing it for scandium, it would be argon followed by 3d1, 4s2. And now this really is a slide that is packed with all kinds of happy goodness, because this is the punchline to the whole business. If you hadn't figured it out before, here's group 1. How many valence electrons are there for everything in group 1? Well, everything in group 1 has a valence configuration of ns1, right? N being whatever period we're in, or principal energy level we're in. So everything in group 1 has a valence configuration of ns1. Everything in group 2 has a valence configuration of ns2. Everything in group 3, as I like to call it, not group 13, but group 3, has a valence configuration of ns2 np1. Group 4, ns2 np2. Group 5, ns2 np3. Group 6, not counting the transition metals, ns2 np4. Etc. So this is how and so this is one of the critical things when it comes to understanding why everything in the same group has the same number of valence electrons. It's because everything in the same group has the same electron configuration at the valence level. Okay, here's another thing that is sort of, this may blow your mind as well. You can work out an electron configuration by writing an electron, an orbital energy diagram, and then populating it with electrons, and then turning that into an electron configuration notation. But there's a simpler way, which is just to simply look at this at the periodic table as being laid out like this. All the elements over here in groups 1 and 2, and that would include helium, are in the process of having their ns orbital filled. All the elements over here in groups 3 through 8 are in the process of having their np orbital filled. So we call these two blue columns, groups 1 and 2, the s block, and we call this groups 3 through 8 the p block. All of the transition metals are in the process of having their d orbitals filled. And then all of the intertransition metals, that is the lanthanides and the actinides, are all in the process of having their f orbitals filled. And so rather than drawing out an orbital energy diagram and then populating that with arrows and then turning that into an electron configuration notation, all you have to do is find where the thing is in the periodic table that you're talking about, and then just do it that way. So let's say we're going to go for, let's say we wanted to do bromine. So we have to locate bromine in the periodic table. Well, it's right here. And so that's the position of bromine in the periodic table. Now I'm just going to go through and say, what do I have to do to get there? 1s, 2s, 2p, 3s, 3p, 4s, 3d, and then I start on the 4p's and I put 5 electrons in the 4p. So all I'm doing is just reading off the periodic table to write this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 1, 2, 3, 4, 5. There you go. I didn't have to sit there and draw out a whole orbital energy diagram and populate it with arrows. I just walked my way through the periodic table with the understanding of these sort of block, this sort of block layout. And if I want to write that with the noble gas configuration, it would simply be argon followed by, so argon is right here, followed by 4s2, 3d10, 4p5. Okay, let's just finish up by talking about the difference between ground states and excited states. We've talked about 3 different rules. We've talked about Hund's rule, we've talked about the Pauli exclusion principle, and we've talked about the Aufbau principle. Turns out that there are some of those things that can be violated, and because a few of those things, a couple of those things are just related to whether or not the thing is at its lowest energy state possible, not whether or not it's obeying or disobeying the laws of quantum mechanics. So let's just go through this, and let's just do an easy example of oxygen. Here I have given you the ground state electron configuration of oxygen in an orbital energy diagram. Well, what about this one? What's the difference between this and this? Well, what I've done is I've taken this electron here and I've moved it up into a 3s orbital. Can I do that? Yeah, I can do that. That is a higher energy configuration, but that's the way we get these emission spectra, right? When we run electricity through oxygen gas in a partially evacuated tube, that's exactly what happens. It starts promoting electrons into higher energy states, and then as they relax back into the ground state, that's when they give off photons of light. So there's nothing wrong with this. I have violated the Aufbau principle here, but that's exactly, every time you run electricity through a neon light, you are violating the Aufbau principle, right? You are promoting electrons into higher states, and then they're relaxing back down and giving off light in the process. So there's an example of promoting 1 electron into a higher energy orbital. I can promote 2 electrons into a higher energy orbital. This is just a really excited state, right, in which I've now taken 2 2p electrons and put them up into 3s. I could also do something like this. This violates, so these 2 things are violating the Aufbau principle. I'm not putting these electrons into the lowest energy orbital possible. Here I'm violating Hund's rule. Well, again, violating Hund's rule, all that does is just put me in a higher energy state, but it's not violating any laws of quantum mechanics. So this is also an excited state. And so excited states violate the Aufbau principle and or Hund's rule. That simply has to do with how much energy there is in the system. And this is how we generate line spectra. So there's nothing illegal about this. It's simply not the highest energy state. Let's contrast that with what are called non-allowed states, because the Pauli exclusion principle is actually one of the fundamental laws of quantum mechanics. And the Pauli exclusion principle is that no two electrons in the same atom can have the same 4 quantum numbers. So let's go back to the ground state configuration of oxygen. This is a happy oxygen atom. It is not violating anything. What if I take this electron and flip it over? Well, I can't do that because now these 2 electrons have the same 4 quantum numbers. And so the Pauli exclusion principle is fundamentally different than Aufbau and Hund's rule. The Pauli exclusion principle is one of the fundamental laws of quantum mechanics, and it cannot be violated. So this is a non-allowed state. It cannot exist. You'll remember on the previous slide, I had promoted 2 electrons. Well, as long as they have opposite spins, that's fine. But I can't promote 2 electrons and make it look like this. This is a non-allowed state because this is violating Pauli. I can't take one of my electrons and push it down into the 2s so that I've got 3 electrons at the 2s level because these 2 electrons are violating the Pauli exclusion principle. They have the same 4 quantum numbers. You can never have more than 2 electrons in a given orbital. So you cannot violate the Pauli exclusion principle. So you can violate Aufbau and Hund. That gives you an excited state, and that's how we generate light, by running electricity through these things. You cannot violate Pauli because that is one of the fundamental laws of quantum mechanics. So none of these 3 configurations can exist. It's not that I won't let you write them. They literally cannot exist in the universe. Well, let's just go for one last problem here. I think at some point I've written problems that have to do with whether or not a particular configuration was allowed. I couldn't find a problem like that, but I did find this problem in the test bank for chapter 6, which is, and we were just talking about oxygen, so this is a good example. Which one of the following configurations depicts an excited oxygen atom? Well, here's how I would solve this. I would ask myself, first of all, what is the ground state for oxygen? And in my mind, I can just write this out. It's 2s2, 1s2, 2s2, 2p4. That's D. So D is not an excited oxygen atom. D is an oxygen atom in the ground state, so D is out. E is the same as D. It's simply the 1s2 being replaced by a helium core. And so E is out because D and E are the same thing. They're both the ground state. Then I just start counting electrons. An oxygen atom has 8 electrons. C has 2, 4, 5 electrons, so that's out. A has 2, 4, 6 electrons, so that must be out. This leaves us with B, 1s2, 2s2, 2p2, 3s2. It's got a total of 8 electrons, but it's not the ground state. It's also not violating the Pauli exclusion principle. I don't have 3 electrons at any p subshell. And so the answer is B. And in fact, B is, if we work our way back, is this right here. 1s2, 2s2, 2p2, 3s2. That is an excited oxygen. Okay, thanks for watching, and we will talk to you soon.